For generations, Pluto was treated as the forgotten frontier of our solar system. It appeared to be nothing more than a tiny, frozen speck drifting in permanent darkness far beyond Neptune. Astronomers knew its orbit, estimated its size, and assumed it was an ancient world that had long since become inactive. Few imagined it could still hold any major surprises. Everything changed when NASA's New Horizons spacecraft reached Pluto after traveling through space for nearly a decade. The mission lasted only a few hours as the spacecraft sped past its destination, but those precious moments completely transformed our understanding of this distant world. Instead of finding a lifeless ball of ice, New Horizons revealed an extraordinary landscape. Towering mountains made of solid water ice stretched across the surface, while vast plains of frozen nitrogen looked surprisingly smooth and youthful. Scientists were stunned to discover terrain that appeared far younger than expected, suggesting that Pluto had remained geologically active much longer than anyone had believed possible. Perhaps the most breathtaking surprise surrounded the dwarf planet itself. Layers of bluish haze floated high above the surface, forming an atmosphere unlike anything scientists expected to see so far from the Sun. Even in the dim sunlight of the outer solar system, complex chemical reactions were taking place. But New Horizons had one major limitation. It was designed for a single flyby. Once it collected its images and measurements, it continued deeper into the Kuiper Belt, leaving Pluto behind forever. Humanity had received only one close inspection, and many questions remained unanswered. Researchers wanted to know whether Pluto's atmosphere changed over time. They wanted to understand how its strange haze behaved, how heat moved through its thin layers of gas, and whether the planet's climate was more dynamic than anyone had imagined. Those answers would require a completely different kind of observatory. Years later, the James Webb Space Telescope turned its powerful infrared instruments toward Pluto. Unlike New Horizons, Webb did not capture close-up photographs. Instead, it examined the faint heat radiating from Pluto across billions of miles of space. By studying infrared light invisible to human eyes, Webb could investigate the chemistry and temperature of the dwarf planet in remarkable detail. What the telescope revealed surprised researchers once again. On many planets, atmospheric haze helps trap heat, acting much like a blanket that keeps the lower atmosphere warmer. Pluto appears to behave in the opposite way. Its haze seems to absorb the small amount of solar energy it receives before releasing that energy back into space as infrared radiation. Instead of warming the atmosphere, the haze may actually help cool it. In effect, Pluto's atmosphere functions more like a giant radiator than a greenhouse. This discovery suggests that Pluto operates with a climate system unlike any other yet observed in our solar system. Rather than simply being cold because of its enormous distance from the Sun, the planet may actively regulate its own atmospheric temperature through the behavior of microscopic haze particles. That realization changes far more than our understanding of one distant dwarf planet. Pluto's atmosphere forms through interactions involving nitrogen and methane. Weak sunlight breaks apart methane molecules high above the surface, allowing them to recombine into increasingly complex organic compounds. Over time, these tiny particles accumulate into the hazy layers surrounding the world. Scientists believe similar chemical processes could occur on other icy bodies, including Neptune's moon Triton and Saturn's moon Titan. Some researchers even compare aspects of this chemistry to conditions that may have existed on the early Earth billions of years ago, making Pluto an unexpected laboratory for studying atmospheric evolution. Although Pluto is far too cold to support life as we know it, the formation of complex carbon-rich molecules demonstrates that sophisticated chemistry does not require warm temperatures. Even in one of the coldest regions of the solar system, nature continues to build increasingly complicated compounds. The more scientists examine Pluto, the harder it becomes to describe it as a frozen relic. Its atmosphere remains active. Its surface displays signs of ongoing change. Ice behaves in unfamiliar ways under extreme temperatures, and chemical reactions continue despite the weak sunlight reaching the distant world. The sun shines so faintly at Pluto's distance that daylight would resemble deep twilight on Earth. Temperatures are so low that nitrogen, the primary ingredient of Pluto's atmosphere, can freeze directly onto the surface. Water ice becomes harder than granite, creating mountains that can stand for millions of years without melting. Despite these extreme conditions, Pluto is anything but chemically inactive. High above the surface, sunlight slowly breaks apart methane molecules suspended in the atmosphere. The fragments collide with nitrogen and other gases, gradually forming larger and more complex compounds. Over countless years, these particles gather into countless microscopic grains that drift through the atmosphere, creating the bluish haze first photographed by New Horizons. For a long time, scientists viewed this haze as little more than a visual curiosity. It looked beautiful, but its purpose remained unclear. James Webb's infrared observations changed that perspective. By carefully measuring the heat escaping from Pluto, researchers found evidence that the haze itself may control the temperature of the atmosphere. Instead of trapping warmth, as clouds and greenhouse gases often do on Earth, Pluto's haze appears to absorb energy before releasing it back into space. This constant loss of heat could explain why Pluto's atmosphere remains colder than previous models predicted. If this interpretation is correct, Pluto possesses a climate unlike any previously confirmed in our planetary neighborhood. Rather than being shaped primarily by sunlight or greenhouse effects, its atmosphere may be regulated by suspended particles acting as an efficient cooling system. That discovery reaches far beyond Pluto itself. These discoveries also force astronomers to reconsider the countless icy objects scattered throughout the Kuiper Belt. For decades, many of these distant bodies were assumed to be inactive leftovers from the formation of the solar system. Pluto now suggests that assumption may be far too simple. If one relatively small world can maintain unusual atmospheric chemistry and an unexpectedly complex climate, then countless other distant objects may possess hidden processes that have never been observed. Rather than representing the end of the solar system's story, Pluto may be opening an entirely new chapter. Instead of marking the boundary between familiar planets and empty darkness, it has become a reminder that even the most remote worlds can remain active, evolving, and scientifically fascinating. The farther astronomers look, the more they realize that distance does not necessarily mean inactivity. Sometimes the greatest surprises are waiting in places once dismissed as too cold, too small, or too distant to matter. And Pluto may be only the beginning.